Hello friends, this video on surface chemistry part 14 is brought to you by examfear.com. No more fear from exam. Now let's talk about some of the properties of solid catalyst. And here I'm talking about solid catalyst mainly heterogeneous. So now if you see, what is activity of a solid catalyst? See, activity of a solid catalyst is nothing but ability of a catalyst to increase the rate of reaction. Ability of catalyst to increase the rate of reaction. This is my reaction going on, right? Hydrogenation of oil, let's suppose. So there's a nickel catalyst, it increases the rate of reaction, correct? So that is my activity of this catalyst. And this activity of this catalyst will depend on what, if you see I'm talking about heterogeneous catalyst, the one thing that is critical here is adsorption. Because on these nickel catalysts my hydrogen will get adsorbed, right? So it depends on the strength of adsorption. So the reactants must be adsorbed reasonably strong on this catalyst, right, to become active. So adsorption is the key here, but the adsorption should be fairly strong. It shouldn't be very strong, right? If it is very strong, then for example, if it is very strong, the adsorption, if suppose hydrogen is adsorbed on this nickel metal, and if it is not able to go off back, it's a problem, right? Because the whole mechanism is my reactants are adsorbed, complex is formed, the product is formed, and it goes back. It has to leave the surface for other reactant to come, right? But if it is if the adsorption is very strong, then it is a waste. So it has to be reasonably strong, right? Adsorption has to be reasonably strong. Correct? Because too much adsorption is also not good, because in that case the deadsorption will have a problem. The product or the reaction will not be able to leave the catalyst surface. But we want that also, right? So it has to be reasonably strong. So it is found that the catalytic activity for hydrogenation, I'm talking only about hydrogenation, so it increases from group 5 to group 11. So if you see group 5 to group 11, if I'm talking only about hydrogenation, that means if I'm talking about hydrogenation, I'm talking about adsorption of hydrogen, right? So this is seen that, for example, here the group 5 elements will not be able to adsorb more, but group 11 elements, for example copper, will be able to adsorb more, right? So the activity of adsorption of hydrogen increases from group 5 to group 11. And the best is seen in group 9 and 10. And that's why we see platinum is here, nickel is here. Both these palladium is also used. So cobalt is also used. So most of the catalysts we use in our labs are part of group 9 and 10 only. This part only. 9 and 10 shows the maximum activity. I'm talking about hydrogenation. That means I'm talking about adsorption of hydrogen. Correct? See, now one good example I can say is, for example, I am hydrogen and water. Very good example of activity of water. Hydrogen and oxygen, it should react to form water. But typically if you mix hydrogen and oxygen for years, nothing will happen. Nothing will happen. But the moment no reaction, actually, nothing will happen. But hydrogen and oxygen only in the same chamber, you just put a small amount of platinum. It is actually explosive reaction. It happens very fast. It explodes. So if you see, small amount of catalyst is changing the reaction so much. Correct? Tungsten is again a catalyst. It will increase the rate of reaction for the decomposition of ammonia. If we talk about the decomposition of ammonia, this tungsten will increase the rate of reaction by 10 to the power 32. It will increase this rate of reaction by 10 to the power 32. Such a huge number, right? And they're not being consumed in this reaction. You can reuse it. Correct? Such a huge importance in the industry. These reactions are, this catalyst really plays a huge importance. Their activity is really very, very important in certain reactions. Yeah, one more thing I want to tell before I end this activity of this solid catalyst. See, these catalysts will work only for a spontaneous reaction. If delta G for a reaction is less than 0, if it is delta G is less than 0 for a reaction, then only my catalyst will work. If it is a non-spontaneous reaction, catalyst won't help, because see, if it is non-spontaneous reaction, that means the reaction won't happen, right? But if it is a spontaneous reaction, that means the reaction will happen. The speed you don't know. It may be a very slow reaction. For example, carbon diamond changing into carbon. It's a very slow reaction. Or even you talk about the rusting of iron, is slow reaction. So yeah, these are my spontaneous reactions. Spontaneous reaction doesn't mean it has to happen immediately. It means the reaction is feasible, right? But the reaction rate may be slow. So these catalysts only increase or decrease the rate of reaction. So if the reaction is feasible, then only these catalysts can help. That means if delta G is less than 0, that means the reaction is feasible, then this catalyst can help to increase the rate of reaction. But if delta G is greater than 0, that means the reaction is not feasible, then these catalysts won't help much. Right? The next feature of the solid catalyst is selectivity. Right? What I'm saying is the ability of the catalyst to affect the desired reaction and prevent other side of the reaction is called selectivity of the catalyst. See, one catalyst will impact only one reaction or two reactions, right? It won't impact everything. And this selectivity is very important when you design medicines, because when you design medicines, it impacts certain reactions in the body. It doesn't impact other reactions in the body, right? So this selectivity of a solid catalyst is very important when you design medicines. If you talk from a reaction perspective, so for example, I have a CH3, CH2, OH, ethyl alcohol. If I use nickel as catalyst, I am getting this product. The same ethyl alcohol, when you react in this presence of Al2O3, you get ethene and water. So if you see, the input was same, but the catalyst made a difference. One more example I can give you. Let's take HCOH, use Al2O3, it will break into water and carbon dioxide. You take the same HCOH, use zinc oxide in this case, it will break into hydrogen and carbon dioxide. Same reactant, different catalyst gives a different product. Carbon, if you take hydrogen and in the nickel catalyst, with this reaction you get methane and water. Again, same thing, CO, carbon monoxide, and I react with hydrogen. Instead of nickel, I have copper or ZNO actually, and Cr2O3. This will give me CH3OH. The same thing again, carbon monoxide and hydrogen in presence of copper will give me HCH. So you see here, same reactant, different catalyst gives different. Right? Thus you can see that the action of catalyst is highly selective. Right? A given substance can act as catalyst only in a particular reaction. See, nickel will not act as catalyst in, for example, sodium plus chlorine gives sodium chloride. So there nickel will not have any role to play. So these catalysts, these substances actually act as catalyst only in particular reaction, not in all reaction. The next property we will be studying is the shape selective catalysis, and these are done by zeolites. See, zeolites are what? Zeolites are metal silicates. And this is the example of zeolite. This is zeolite. They are either natural zeolites or you have artificial zeolites also. They are nothing but metal silicates. They are used as ion exchanger to remove hardness, right? And these have peculiar shape. You see, they have a peculiar shape, and because of this shape, they are used for shape selective catalyst also. But generally, the zeolites are used for as ion exchanger. We have discussed this in one of the chapters. I remember for purification of water, zeolites are used, right? But that is the main usage of zeolites in the market today. But they are also used as selective catalyst because of their special shapes, right? They are microporous aluminosilicates. So their general formula, if I want to write for this zeolite, it is nothing but M some X by N. Now I have AlO2 some X, SiO2 some Y, again to the power M dot H2. There is M here. That is the general formula of silicate, right? So they are open structures of silica in which aluminium has been substituted in some of the fraction of the tetrahedral sides. So they are basically nothing but silica. And silica, some of the traces of aluminium are there, right? And they are good shape selective catalyst. Why? Because they have a special structure, honeycomb structure. You see, they have a different kind of structure. And these, if you want to define the term selective catalysis, I'll say that this catalytic reaction that depends on the pore structures of the catalyst and the size of the reactant and the product are called shape selective catalysis. Correct? So what is this? Catalytic reactions. These selective catalysis is nothing but reactions or catalytic reaction that depends on pore structure of catalyst. Pore structure of catalyst. Right? If it depends on pore structure of catalyst and also obviously the structure of my reactant product, this is called selective catalysis. Right? So as I told, zeolites are microporous aluminosilicates and it has a 3D network. You see, there is a 3D network of silicates in which some silicon atoms are replaced by aluminium. So I can say that it has aluminium oxygen silicon network. That is what my zeolites are. So since they have a very typical structure, a very characteristic structure, the reaction which takes place in this zeolite depends on again the structure of zeolites and the size and shape of the reactants. Correct? And these zeolites are widely used as catalysts in petrochemical industry. In petrochemical industry. And they're used for cracking hydrocarbon and isomerization. Correct? So a good example I can give for zeolite is ZSM5. This is zeolite and this is used to convert methanol, that's again alcohol, to petrol. So I have a methanol to petrol. Petrol is nothing but gasoline. Right? It is used to convert methanol to petrol. This is ZSM5. Sorry, this is ZSM5. This is a catalyst used to convert methanol to petrol. Right? And this is done by dehydrating this methanol. Correct? So this is methanol if you want see nothing but CH3OH. So if you dehydrate, you may get CH4, right? Or you may get, actually with this you get carbene. If you remove water from this, what you get is carbon. Now these carbenes can actually combine. These carbon can combine with hydrogen to form CH4. Two of these carbon can combine to form C2H6 and it can also form C4H10. Correct. So with this you get mixture of hydrocarbons and this is called gasoline. So this ZSM5 is a synthetic zeolite. If you want the formula of this is nothing but H56 AlO2, 66 SiO2, 40.16H2. This is the formula of ZSM5. The zeolite, synthetic zeolite is used to convert methanol to petrol or gasoline. Nothing but a mixture of different kind of petrols, diesel, everything combined. You get the crude form is called gasoline. So the way it works is this is methanol. With this zeolite, water is removed, dehydration take place. You get carbon, and this carbon is little reactive. This is the reactive carbon. It's very unstable actually. These carbon forms methane, ethane, propane, and stuff like that. So this is selective catalysis by zeolite. They have peculiar structure. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.